All right, what's going on, everybody? We are here on the second video of week 13. We've been talking about our chi-squared tests, and today we're going to carry on with that. We're going to get two new chi-squared tests, and the good news for us is that the calculations associated with them are going to be very, very closely related, so we're going to have some pretty similar calculations going on. We've got really two different scenarios that we want to set up. The two tests that we're looking at today are the tests for independence and for homogeneity. And what I know is it's not directly obvious what it means to test for independence or test for homogeneity. So let's talk about that real briefly first. So when we are testing for independence, we would like to know if two variables are independent of one another. And so in our first example today, we'll ask the question, uh, we'll look at the relationship between whether or not a person has tattoos and whether or not a person smokes cigarettes. What we might want to ask ourselves is, if I know that a person does smoke cigarettes, does that influence the probability that they have a tattoo? And if the answer is yes, if you think you're more likely to have information about one variable knowing the other, then we would say that those variables are dependent upon one another. However, if there's absolutely no relationship whatsoever between knowing a person having a tattoo and their probability of smoking cigarettes, then we would say that those variables are independent of one another. And what we'd like to do is perform a statistical test to determine if two variables are in fact independent of one another or not. In our second test for the day, our test for homogeneity. For two things to be homogeneous means to be well mixed. The prefix homo means same. And so really what we're looking for here is asking the question, do two variables have the same, or excuse me, that was, I misspoke right there. Two samples of one variable is what we're looking at right here. We are asking if over one variable, two different groups have the same distribution associated with that variable. Um, so in our second example for the day, we're going to ask the question, do males and females have the same distribution of living arrangements while they're in college? Living at home, living in a dorm, living in an apartment, stuff like that. So we want to say, is the distribution of males' living arrangements the same as the distribution of females' living arrangements while they're in college? We might see that males and females have the same distribution of living arrangements or a different distribution of living arrangements. We can test this with a chi-squared test. So our big distinction for the day, because our calculations are actually going to align to be almost identical, is that when we are testing for independence, we are looking at two variables across a single population, right? One population of people, Eurekaans, two variables, smoking status, tattoo status. On the other hand, when we are testing for homogeneity, we're collecting two samples, right, from two different groups, males and females, of one variable. What's your living situation in college, right? So the setups are slightly different here. Our conclusions are going to be different. But the way that we're going to perform our calculations for these two different tests is going to match up to be essentially identical here, which is really good news for us as far as what we've got to remember. Right? So let's hit our test for independence first. All right. So suppose we're wondering if people that smoke cigarettes are more likely to have tattoos or related questions like that. Right. We sample 52 people and we ask them, hey, do you have a tattoo? And hey, do you smoke cigarettes? And we're going to get these following responses. And by the way, we're sort of considering tattoo to be a categorical variable. Either you have at least one or you do not. And you either smoke cigarettes or you do not. All right. So these are yes, no categorical questions that we're asking here. So we're saying we're doing a test for independence. We're saying things like, does knowing that a person smokes help you predict whether or not they have a tattoo? And let's go ahead and look at our table. And certainly I made this data up right here. This is maybe a little exaggerated, but here's what I'm saying. Does knowing that a person smokes, okay, first part of the sentence right there, knowing that a person smokes, that means that we're looking at the yes column right there. Knowing that a person smokes, does this help you predict whether or not they have a tattoo? And based on this table that we're looking at, I'm going to say definitely yes. It looks like of the cigarette smokers, it looks like there's almost twice as many that do have a tattoo as don't have a tattoo, right? If that was 16, we'd have exactly twice as many with tattoos as without tattoos right there. Very similarly, if you knew that a person didn't smoke, it looks like there's more than twice as good of a chance that they don't have a tattoo than if they do right there. So I'm just looking at my bare eyeball observation of this before we get started. It seems to me like the answer is yes, these are dependent on one another, because what I'm seeing is if I knew one of the pieces of information, for example, smoking status, that would heavily influence my prediction as to whether or not they have a tattoo. And notice similarly, if I knew that a person had a tattoo, I certainly see, based on the observations in my table, it seems like they are more likely to be cigarette smokers if they have a tattoo than not. And again, I just made this data up. I don't quite know if this is true or not right here, but I think that this is sort of a thing that we can like visualize for ourselves right here, right? So when we're talking about these being independent, we're asking, does knowing information about one of the variables give you additional information about the probable value of the other variable? And I think here it seems like that is definitely the case. And I'll just do one more. If I knew that a person, okay, I'll do the one I haven't do. If I knew that a person does not have a tattoo, then it seems like I can see here that 21 out of 29 people without tattoos do not smoke cigarettes. So it seems like if somebody said, hey, listen, I don't have a tattoo, do you think I smoke cigarettes? I would definitely guess no. And I think that I have a more than 50% chance of being correct. I have additional information about the variable I don't know about because of the variable I do know about. These are intertwined variables. They are dependent upon one another. Knowing the value of one helps you know the value of the other. So I'm expecting that at the conclusion of this example, we are going to be concluding these are dependent, or no, they are not independent. But that's not based on any math right there. That's just based on my like eyeball observations. Obviously, we want to actually compute a value that will make this decision for us. Remember, all of our hypothesis decision or all of our hypothesis testing is helping us make statistical decisions rather than just guessing based on looking at data. So I did make a guess. We should make guesses, but we should trust the math more than our guesses here. So again, our good news is we're always going to keep on following these same 4 steps for our hypothesis test. Form your hypotheses. After we've performed the experiment, we compute a test statistic. We use the test statistic as test statistic, remember, is our z, t, or chi-squared value. We use the test statistic to compute the probability of having observed that test statistic. And if that probability is so extreme, it's beyond our threshold of weirdness, then we say, you know what, that was such a crazy sample, I actually think the null hypothesis is true, right? So same 4 steps. Hypothesis, test statistic, p-value, compare and conclude. Same 4 steps. Our hypotheses for all of our tests of independence are going to essentially look exactly like this. Obviously, our variables are specific to this example right here, but it's always going to state each of the variables that we captured from our one population are independent of one another. Alternatively, what we are suspicious that we might be showing is that there's actually some dependency between these variables. I think, based on just looking at this table, that we will end up rejecting the null hypothesis that they're independent and end up concluding that they are dependent on one another. Because I think according to this table, I think that if I know your smoker status, that will help me predict your tattoo status, things like that. Computing our test statistics. So previously, in our previous video, in our goodness of fit test, when we asked, does our sample follow a proposed distribution, we determined the expected number of counts associated with each cell in our table, and we compared them to the observed number of counts in each cell in our table, and we computed our overall test statistic by adding up. Remember that this big Greek letter right here is a sum. It says add up all of the observeds minus expecteds squared divided by the observed count for that individual cell. So for each of the cells in the table, we compute this number. And this Greek symbol is a sigma here that says, and then add up those, when we did the dice rolling in the last video, there was 6 cells. So we computed O minus E squared over E for all 6 of the cells. And then this sum said, add them all up. And that is what we are referring to as our chi-squared test statistic here. So we're going to do the same thing here. This is still going to be how we're going to compute our test statistic. But the thing that's changed is that it's no longer as obvious to us how to compute this expected value right there. We know what our observed values are. These are the 4 values that O will take on in our computation there. We need the 4 values that E will take on in our computation there. So our new thing for today isn't that we're getting a new test statistic. It's that what we're getting that's new is how to compute the terms required for our test statistic, right? So the only thing that's really getting updated today is just how do you compute the expected counts in a test for independence. So what we're going to do is we're going to come back to remembering our null hypothesis. Remember that in every hypothesis test that's ever performed, we're always doing all of the math with the assumption that the null hypothesis is true. We're always kind of suspicious that the null hypothesis is false. So if we assume the null hypothesis is true and our calculations take us to a crazy place, that's good evidence that our null hypothesis was actually probably false if we get taken to a very crazy place, a very unlikely probability. And that's what leads us to reject it, right? So we're always doing our math with the assumption that it's true, so that if it weren't true, our math should take us to a crazy place and we can identify that with probability. So remember that our null hypothesis says that our variables are independent of one another, and that we're always assuming the null hypothesis is true when performing our calculations for any hypothesis test. Here, we'll need to know things like, if smoking and tattoo are independent, what is the probability that a person is both a smoker and has at least one tattoo? That's exactly what's happening in this cell right here. This is what I want to know is, what is the probability that a person both smokes cigarettes and has a tattoo? And I can use that to fill in my expected value in place of the observed value right here. So this means what we're trying to do is compute things like a probability that looks like this generic probability statement, probability of A and B. In our case, is the probability of being a smoker and having a tattoo. Right? So we want to compute probabilities that look like P, A, and B. And if you remember, we covered this chapter about 6 chapters ago. Recall from our chapter on probability these two distinctions. If A and B are independent of one another, then the probability that A and B are both true is the probability of A times the probability of B. We just multiply their individual probabilities together. However, if these two are dependent on each other, what we're not assuming right now, but what we're suspicious we're going to show is true, then the probability of A and B, this is where we compute the probability of A, but then when we compute the probability of B, we need to know that A has occurred, right? This is me saying, but given that they're a smoker, now what's the probability that they have a tattoo, right? That maybe changes based on that given information. In our lamer examples, in our probability chapter, we said, what's the probability that you pull a green and green marble if you're pulling 2 green marbles? And we said, oh, if we're pulling them without replacement, where it's dependent, then it will be the probability of drawing a green times the probability of drawing 1 green given that 1 green has already been drawn, right? So we saw a lot of the marble examples, I think, with this dependence, independence, with this with replacement, without replacement stuff, but we're getting a similar flavor for it here. In any event, our situation for ourselves is that we are under the assumption, the null hypothesis says the 2 variables are independent, so that says to us we should be using this formulation for our probability statements here. This will help us compute our expected observations. So returning to our table, we can see how we can compute such a value. So what I'm going to do is I've got our observed table over here. This is just copied down from above. What I'm going to attempt to compute is an expected table over here of what values would we expect if, in fact, these truly were independent of each other. All right. So in our case now, we have that the probability of, so for example, we're now looking at the first cell in our table. This is the cell associated with being a smoker and having a tattoo. It's the 2 yes parts, right? This should be the probability that you're a smoker times the probability that you have a tattoo. And what we're going to need here is we're going to need to know information like what's the total number of people with tattoos, without tattoos, total number of people that smoke, total number of people that don't smoke here. Determining your marginal distributions is a very, very valuable thing in these cases over here. So just to help me with my math, the first thing I'm going to do right now is compute my sums here. I see that in total, 24 people that I observed had a tattoo. In total, 29 people did not have a tattoo. In total, 23 people did smoke cigarettes. And in total, 30 people did not smoke cigarettes. Wait a minute, did I count these up wrong? Is that really 53 people? Oh my gosh, I can't do my addition here. I'm going to go back and change my, since I get embarrassed by these things there. 53 people apparently were asked right here. And when I say I know it's 53, all I'm doing is you can either add up all 4 things in the table, or add up the sum of your columns, or add up the sum of the rows, and in any event, we're going to get here that n equals 53 in this case, 53 total observed people. So again, one of your step ones in these situations pretty much is always add up your rows, add up your columns, get your total observed count if it wasn't given to you right there. So here's what I'm going to do. I'm going to compute the probability of being a smoker and having a tattoo. What I'm thinking is it should be some number out of 52 that I expect, or now I got to change these right here. It should be some number out of 53 that I expected to see right here. I'll have to change my computed value over here now. And so what I'm seeing is this. What I'm expecting to see, this is my expected value right here. And in fact, I'm just going to do this. I'm just going to change that to E. There's an expected count out of 53 that I should be expecting to see. If it is in fact true that these two variables are independent of each other, and again, I don't really care if it's true or not, we're assuming it's true for the purpose of our calculations. Then what I'm seeing here is the probability of being a smoker, according to our observations. The probability of being a smoker is 23 out of 53 people were smokers, so that's my first term in my calculation. I can also see that 24 out of 53 people have a tattoo. So it looks like, according to my observations here, the expected count out of 53 should be the probability in my table of being a smoker. What proportion of people in the table were a smoker? 23 out of 53 of them. What proportion of people in my table have a tattoo? 24 out of 53 of them have them. So therefore, the probability of both being a smoker and having a tattoo, if they're independent, should just be the product of these two things. So notice algebraically here, all I'm going to do to solve for E is I'm going to multiply both sides of my equation by 53. That's going to, in a sense, cancel that 53 with one of those ones right there. And you can see that what we're left with is 23 times 24 divided by 53. And very importantly, notice that in general, our expected count here, what was 23 in reference to 15? It was the row total associated with 15. What was 24 relative to 15? It was the column total associated with that cell. And what was 53 here? It was the total, right? So I like to think about this as the row total times the column total. And then I sort of verbally, jokingly refer to this as the total. Right, that's what we just did to get exactly this computation there. And where this came from was our probability rules about independence versus dependence, right? This is really where that probability statement came from. The probability, how many do I expect to be in this cell? I expect it to be the probability that we're in this column times the probability that we're in this row. If they're independent, that'll be true, right? So let me go ahead and update that number because I had that over 52 or 54 a second ago. So I'm getting here 23 times 24 divided by 53, and I'm getting 10.42. So what we can do now is we can compute the expected counts in each cell. If these were independent variables, we should be able to compute the expected counts for each of the four cells here. So 10.42 goes there. And let's go ahead and fill out the rest of these right here. So probability of being a smoker and no tattoo. So smoking is yes. Tattoo is no. So we are now interested in, for our second one, and I'll just number these in the order that we're computing them right here. 1, 2. Our third one will be non-smoker and tattoo. Non-smoker and yes, tattoo. That'll be our third one. And this will be our fourth one right here. So I'll go ahead and number these for kind of convenience. All right. So let's go ahead and compute these now. So now we're looking at cell that I labeled 2 right there. Probability of a smoker and no tattoo. In this case, my row total associated with the cell with an 8 in it, my row total is 23. My column total is now 29. And this is still out of 53. It looks like for all of these, we'll divide by that same 53. Here I'm getting 23 times 29 divided by 53 to be 12.58. And I'll go ahead and throw that in its associated expected table over here. And the next one, probability of non-smoker and a tattoo. Smoke cigarettes, no. Tattoo, yes. So we're now looking at the cell that has the 9 in it right there that I've labeled number 3. We're going to do our row total times column total divided by total. It looks like my row total here is 30. My column total is 24 divided by the total, which is 53. Finally, I'll just write out my calculation for the last one. No smoking, no tattoo. That's going to be associated with the cell with 21 counts in it, observed counts. That should be giving me row total is 30, column total is 29 divided by the total of 53. And let's go to the calculator, get these two, throw them in our table, and we'll be ready to compute our chi-squared test statistic. So I've got a 30 times 24 divided by 53, and I've got a 30 times 29 divided by 53. And I'm getting my two expected counts here of 13.58 and I'm getting 16.42. All right, so 13.58 went here, and 16.42. All right, so these are the counts that I expected to get if I'm going to perform this calculation. And by the way, real quick, notice something cool going on here. Notice that if you add up these two numbers right here, I'm seeing 20, 28, and those two perfectly add to give me 21 to give me 29 total for this column, which is exactly how many we had in that column before. Similarly here, 10 plus 13 is 23, and the decimals add perfectly to 1 to give me 24, perfectly the column total here. We're going to get the same match for the row totals. 13 and 16 is 29. Their decimals add to give 1, which is 30. So these do match their row and column total expectations relative to the observed table, our expected table over here. All right. So what we can now do is we are now able to compute our chi-squared test statistic because I know all of my observed values and I know all of my expected values if the null hypothesis were true. Real quickly, a naming thing here. I didn't name this last video, but then I noticed that all of the homework problems in My Open Math reference it as such. A squared Pearson residual is just our O minus E squared divided by E term. Each of those individually is referred to as a single squared Pearson residual. The sum of the squared Pearson residuals is what we call our chi-squared test statistic here. So that's just our name for that little expression that we use to compute our the terms that we need here. So what I'm going to say here is our sum of the Pearson's chi-squared residuals, O minus E squared over E. We want to add up all of these guys. So what do we got? I'm going to do a little bit of up and down scrolling here, but we'll make it. First is our yes grouping. Our observed was 15, expected 10.42. Oh, forgot already. 15, 10.42. 15, 10.42 over 10.42. That's our first, this is our first Pearson square residual right there. Squared Pearson residual, there we go. And we're adding up these for each of these guys here. So what were my, so we'll do these in order. 1, 2, 3, 4. So 8, 9, 21. Oops. All right. And our expecteds in order 2, 3, 4 were 12.58, for cell 3, 13.58, and finally 16.42. All right, so here is our sum of all of the O minus E squareds over E, and we can go ahead and go to our calculators, add these guys up, and we will have our chi-squared test statistic. So let's just say here, chi-square equals that stuff, and we're going to get here then chi-squared equals, and let me, I just want to move this so I don't have to move all of the rest of my writing here. I can get this in here, chi-squared equals. And so I'm going to do these one by one so we can see their individual contributions. 15 minus 10.42 squared divided by 10.42. I'm getting a 2.01. 8 minus 12.58 squared divided by 12.58. 1.67. 9 minus 13.58 squared. Oops, 9 minus 13.58 squared divided by 13.58 is 1.54. And finally, 21 minus 16.42 squared divided by 16.42. 1.28. So what I can see from this, and I need to add all these up to get my chi-squared test statistic, but what I can kind of see from this guy, the reason why I stopped and did all these individually for a moment is because we can see which of these cells has the largest contribution to our measurement of difference here, right? The fact that this 2.01 is the largest of the four squared Pearson residuals says to me, and notice that this was like box one up there, that says to me that box one is the box that deviates the most from its expected value. That says to me right here, box one was the most extreme of an observation relative to the expected observation, or I shouldn't say expected observation, relative to the expected counts if the null hypothesis were true. On the other hand, we can see that the smallest one was this last one, box four. Box four was in most agreements. It's the closest to being in agreement with its with the expected value right there. The observed and expected were the closest match right there. There's the least deviation from what we expected to see in our observation in that box right there. So looking at these is sometimes a very practical thing to say, which observations did we see that were the ones that were unlikely, and which ones did we see were the ones that we expected to have happen if the null hypothesis were true? Here, these I don't see one that's like way, way, way more of a contributor than the other. In this case, it looks like all of them were a little bit off from what we expected right here. So adding these guys up, I'm getting, ooh, wow, that's weird, exactly 6.5. All right. So this is good. We computed our test statistic. Woohoo. And look, the other good thing, it's exactly like we did yesterday. The one thing that changed is we computed our expected values a little bit differently than we computed our expected values yesterday. And it's because we're in a two-way table instead of a one-way table. There's two variables involved, so there's going to be a little bit of a different way that we compute our expectations there. As we saw yesterday, though, we're always still going to need a number of degrees of freedom associated with any chi-square distribution. So remember, and in fact, I think I might as well just pull up that same Desmos graph from yesterday, because why not? Because I feel like that's a thing we should always be looking at here. Desmos chi-square. And by the way, to get this, I'm literally just Googling Desmos chi-square, and it brings up that very nice fancy Desmos graph that we saw yesterday. And so let me bring this over to you. Here we go. Cool. So what's, oh wait, sorry. I jumped the gun on that one right there. We got to look at one piece of information first. To compute the degrees of freedom associated with a test of independence, this is going to be a little bit different. Remember that yesterday when we did things like rolling the dice, there are 6 outcomes when rolling a 6-sided die, and we decided that our number of degrees of freedom was going to be one fewer than the number of possible outcomes. Here we're going to do that sort of similarly, but a little bit different because we're in a two-way table. This instead will be the number of rows minus 1 times the number of columns minus 1. In our case, that was 2 minus 1. There was 2 rows in our table. There was 2 columns in our table. There was 2 possible outcomes for the variable tattoo. There was 2 possible outcomes for the variable smoker. And so that's just going to be 1 times 1, and that's just 1. So in total, we've now found 6.5 was our chi-square test statistic, and that's associated with 1 degree of freedom. So let's go ahead and look out here in our graph to see where this looks. What do we expect to be getting for a p-value here? So if I go over here, then we could take a look at this graph here. I'm going to take my number of degrees of freedom to 1. And what we can see is that getting a test statistic of, oh, there we go, 6.5 right there. It's going to leave me with a pretty small amount of area in the tail right there, right? It looks like a very small p-value. The p-value is in red. My test statistic is sitting there at 6.5. Can I maybe zoom in on this and get a little, okay, I guess what I want to do is, I just want to get the little snippet of this thing so we can actually see it here. And give me better labels here. Why did it make it 2.5? I want it to be 0.5. It did the opposite of what I wanted to. 0.5. That should be my... Okay, apparently it doesn't like me today. That's okay. We can see here, we're going to get this really, really small p-value out there, which again is going to say to us, this seems very unlikely if in fact these variables are independent of each other. This small, small area, and remember, it just struggles to fill it in with the appropriate shading right there. Sometimes I'm not really sure why. But again, the point is the probability is equal to the area underneath the distribution. Here's our distribution curve. The area here is representative of the probability that if we were to perform this experiment again, we'd see results that are at least as extreme as this relative to the null hypothesis being true. If it really is true that these are independent variables, it looks like there's a very small probability that we would have drawn an observation that looks like the stuff that we saw. That's evidence for us, typically, that the null hypothesis probably is not actually correct. So let's come back here and see what we're actually going to get for the p-value. To do this, we're going to go over into Excel, as we did before. Excel. Remember that it's always a right tail that we're interested in for the chi-square distribution. So we're always going to do our 1 minus. It should be chi-square dot dist. It's always going to want to know our chi-square test statistic, our degrees of freedom, and it's always going to be cumulative. And let's go pop over to Excel and see what it's going to give us here. Over in Excel. Over in Excel. Here we go. We've got our, let me just say, trying to keep this organized so this will be useful for us. And so we did, our p-value is going to be equal to 1 minus chi-square dot dist. It's prompting me right now for x, which is our chi-square test statistic. That was 6.5. Our number of degrees of freedom is 1, cumulative true. And it's telling me, just like I thought, a really small p-value right there. It wasn't like insignificantly like 0 right there. It looks like there's a 1% chance approximately that if we were to perform this experiment again, that we'd see results at least as extreme as the ones that we saw relative to that null hypothesis. So it looks like our p-value 0.01079. So I'm getting here 0.01079 as our p-value. And now we can go ahead and compare and conclude. And here I can see, and by the way, it looks like I did not suggest a alpha value that's associated with this, right? I'm just going to come back up to read the problem. Yeah, it looks like I didn't state an alpha value here. I still think that this is a pretty extreme result right here. So I'm just going to say alpha wasn't given, but this most likely qualifies as a rare event. So I'll go ahead and say all right. So again, I didn't state a alpha value directly to compare to, but I think, and again, we discussed what these alpha values really mean. If we need to be like really, really, really sure that we're right, if it really matters, that's when we set those very low alpha values, saying it's a very difficult threshold to get over. I don't think determining whether or not smoking status and tattoo status are related is like a super technical thing. I don't think that there's, any brain surgeons out there that are super concerned about that. And so I think that here, that 1%, that about 1.08% chance is a rare enough event that that's evidence, strong enough evidence for me that these should be dependent variables, not independent variables here. So not too bad here. What I'm thinking that you're thinking is this. I'm thinking that you're thinking this wasn't too bad. This is kind of annoying. So in our next example, and also, by the way, I'm going to point out one other nice thing here. This is like the smallest, simplest table I could ever give you. Only two possible outcomes for each variable, a sample size small like 53. It can't get nicer than this setup right here for our by hand math. So in our next example, it's not quite going to be this nice. It's still going to be really nice. But we're going to use Excel like heavily to help us out with the next one because I just don't want to do that much math by hand. All right? So in our test for homogeneity, this is our second test of the day. We just did a test for independence to determine if two variables are independent of one another. We will now do a test for homogeneity. The homogeneity test will take one variable's information from two different groups. That's the big difference here. And we want to ask, are the proportions of responses for this variable the same, or are they different across the two groups? The good news for you is that the test for homogeneity is going to look a lot like the test for independence. The difference is that the two different samples will be drawn concerning one variable, whereas in the test for independence, we drew one sample across two variables. The real big difference is the setup here. This test will ask, are the distributions of a certain variable equal across two different populations? So, for example, do male and female college students have the same distributions of living arrangements? Perform a hypothesis test at the alpha equal 0.05 level of significance. So I actually gave you an alpha value for this guy. So suppose we take a random sample and we find the following results. What we're wondering is the male distribution of living arrangements, does it match the female distribution living arrangement? And before we go into answering this, I want to kind of show you a scenario in which do I have some room right here? I do have some room. I'm going to give myself some room. There we go. So what I'm going to do is I'm going to make a table that's not the one that we're looking at here, but I want to show you kind of how to be careful in thinking about this. Okay, I'm getting myself into a place that, oh no, that's okay because we're gonna let. I still want to give myself some room. Hang on, let me move this guy a little bit here. All right, so I'll just can I hit enter right now? Yes, thank you. So here's the thing I want us to be a little bit careful about. Suppose we ran across a table that looks like this. Would you say that the males and the females, for whatever we're observing, maybe this still is dorm, apartment, parent, other right there, do these have the same distribution or not? What's misleading about this table here is it looks like things don't match up at all between the male and the female rows. I see 6 for the female, I see 2 for the male, right? I don't see any matches between the males and the females. What we are not asking about, though, is were there the same number of observations between males and females? We're asking, does the distribution match? Here, what I'm seeing is, let's see, how many males did we sample here? 2 plus 3 is 5, plus 4 is 9, plus 2 is 11. What I'm seeing here is 2 out of 11 males live in a dorm. What am I seeing over here? 6 plus 9 is 15, plus 12 is 27, plus 6 is 33. And I'm seeing that 6 out of 33 females are in a dorm. Well, notice what 6 out of 33 simplifies down to. It seems to me like the proportions are exactly the same in this table. Notice here, it seems like I just sampled 3 times as many females. All right. So our little like word of warning associated with this guy is to say, don't think that we're looking at counts and asking if the counts are the same. We are asking if the distributions are the same across the two variables. It might be the case that we sampled 3 times as many females as males. Well, in that case, then we should expect to see 3 times as many counts in all of our cells, even if the distributions are identical to each other. All right. So just be a little bit careful in what you think you're looking for here. Let me do here. Um, Right, so notice in this table right here that I made, the distributions are literally identical. If you were to compute your chi-squared test statistic associated with this guy, you would literally get 0 because there is no difference in distribution between these two groups. 3 times as many females are happening in every single grouping right here. So the distribution is exactly the same across both groups. We just happen to sample one of the groups much more heavily than we sampled the other groups. So again, when I say, are the distributions matching? I am not looking here and saying, oh, 72 versus 91, there's more females, it looks like. Maybe we sampled more females in this overall thing, in which case we should expect for there to be more females if they are truly, in fact, distributed the same out there, right? So the thing that I'm really seeing here is this. When I just eyeball this table to make a visual estimate of whether or not I think that there's going to be some major difference or not, what I'm visually seeing for myself is I see that there's approximately equal numbers in the apartment column, but I see very different numbers in the parent column and slightly different numbers in the dorm and other column. So the thing that's suggesting to me that it says to me, yeah, I kind of think that there actually kind of does look to be a difference here, isn't because these numbers are different. It's because some of the numbers are different and some of the numbers are same. Notice here, these numbers all differed, but they differed in the exact same way. One was always 3 times as much as the other one there, right? Just be a little careful in like estimating this visually. We're not saying are the counts of males equal to the counts of females. We're asking are the sort of like the proportions of males. These proportions right here equal to the proportion of females. And in this case, they're exactly equal proportion-wise the entire way across the table. This table here literally has a chi-squared test statistic of 0. There is no deviation from the difference of identical distributions right there. So let's go ahead and actually set this guy up here. Uh-oh, we're back into this situation again. Okay, I'm just going to get dots everywhere on this thing. So our hypotheses, I guess that's coming down here now. Our hypotheses in a test for homogeneity are always going to be the distribution of the variable for the one group is the same as the distribution of the variable for the other group. In our case, the distribution of living arrangements for college males is the same as the distribution of living arrangements for college females, with the alternative just saying that's not true. There's some difference in distribution. To be a little bit more mathematical about this, what's a little bit more appropriate for us to say is, for our distinctions, here's my slightly more mathy version of this, is to say the proportion of males in the dorm is equal to the proportion of females in the dorm. The proportion of males in apartments equals the proportion of females in the apartments, blah, blah, blah. 4 statements for the 4 possible outcomes of the one variable that we collected across the 2 groups. The alternative hypothesis would say at least one of the listed equalities is not true. If one of these is not true, then our distribution does not match because the distribution is the proportions for all of the possible outcomes out there, right? This is our slightly more mathematical way of saying the same thing that we said in words in the grouping up above right here. So I think it's just good to recognize that these are sort of equivalent. This is just a more technical way to say it on the bottom down here. So computing our test statistic, this is always the exciting part. This is the thing that keeps on changing for us. Fortunately for us, it's going to turn out that our calculation to compute this test statistic is going to end up being literally the same as it was in our previous test, but it's going to happen to be the same for a slightly different reason. But at the end of the day, the computation is going to be the same. So let's return to this observed table and use it to compute our first expected value, right? And again, the thing that we're going to want to do in all of these cases here is to always get our sums of our rows and our columns to help us out with this guy. So let me go ahead and find some of these. And by the way, I'm going to just say to you up front, what we're going to do right now is this. We're going to talk about what is the expected value that's associated with this cell in the table, the males in the dorm that currently has an observed value of 72. All the rest we're going to do in Excel. So I'm not going to do a ton of by hand work right here. I'm just going to get my row total and column total so we can do one of these guys by hand here. So I'm going to see here. Oh gosh, just never bring that thing up. How do I turn that off? I'm going to do this column total right here. It looks like it's 163. I'm going to go to my calculator and get the row total for that guy. 72 plus 84 plus 49 plus 45. And that's giving me 250. And I need to know the total also for all these types of things. So I'll also add on the bottom row 91, 86, 88, 35. and it seems like I have a total of 550. So I'm doing my lazy man's work right now because I'm just going to show only one of these computations by hand, and then we'll let Excel do all the work for us because this is going to be a lot of by hand work. The overall process itself isn't that hard, but like we don't want to just sit around just doing multiplication all day. That's not exciting, right? So we're only dealing with this guy right here. Okay? Right, that's our guy of interest right there, 72. So, assuming the null hypothesis is true, we expect to see an equal proportion of men and women college students living in the dorms. We expect the proportions to be the same across male and female. So here is my expected, that MD is I'm saying, what's my expected count of males in the dorm? It's just my attempt at making some notation that makes sense right there. What I'm noticing is that there were 163 total dorm dwellers that were identified here. It therefore seems to me like those 163 should be split evenly across the male and female groups, but proportionally. And notice here, like we sampled 50 more females than we sampled males. So if there is an equal distribution, I expect there to be that little bit more females than males. I think here there's a little bit excessively more females than males relative to this 250-300 breakdown over here, but that's exactly what we're going to see in our expected counts right here. So what I'm going to say to myself is, how many males do I expect to be in the dorm? Well, 250 out of 550 is the proportion of males sampled overall. Out of all 550 people sampled, 250 of them were males. So the proportion of males sampled, right, regardless of living status, the proportion of males sampled was 250 over 550. I'm looking at the dorm category. The dorm category had a total of 163 people observed. So I'm thinking if there really is no difference in distribution across males and females, then it should be that 250 out of 550, that's my proportion. That proportion of 163 should be how many males there are in the dorms, right? The proportion of males times the total of people in the dorm should equal the proportion of males that we expect to live in the dorms. Right? So it's the number of males in the dorm, or sorry, number of people in the dorm times the proportion of male. That's the important part right there. Number of people in the dorms, 163, times the overall proportion of our sample that was male, 250 out of 550, should give us the expected number of just males that are in the dorm if there is a equally likely, or if there is a uniform. All right, try one more time. If the distribution of living arrangements for males is equal to the distribution of living arrangements for females. So notice what ended up happening right here is that these numbers that we're multiplying and dividing, 163 was the column total, 250 was the row total, 550 was the total. So it's not for the same reason. It's for a different reason that we get this computation, but it turns out to be exactly identical to the computation that we were doing before to get our expected counts. So it seems like we're expecting to get, what do we get here? 163 times 250 divided by 550, and that's giving me 74.09. Right? So what that says to me is we expect to see, if there is an equal distribution of living arrangements for males and females, then we should have seen about 74 males living in the dorm. We saw 72 males living in the dorm. That's actually really close to what we should have expected to see right there. It's a very close, that seems perfectly plausible then. So this, in a sense, is one small piece of evidence that says, yeah, there is an equal distribution across the two genders out there. Now, what I know we're going to see in a minute, though, is things like 84 and 86 are almost identical, but there's a pretty good difference in males and females out here. So I think these guys will give us larger contributions. But we got to see, like, it's really tough to eyeball these things, right? So we did compute one expected value. That's the expected value for the upper left corner of our expected table here. And again, this computation is still our row total times column total divided by the total. this formula actually came from a different place. The parts of the formula are a little bit different than we saw in our previous example, but the resulting computation ends up still being row total times column total divided by total out there. So that's really convenient for you that you don't ever have to remember the difference between these two formulas. All you've got to know is if your data comes in a two-way table, then that's how you're going to do it. We saw two-way tables in our test for independence above, and now in our test for homogeneity, we're also seeing these two-way tables, and the computations for computing the expected number of observations is the exact same for both. Um, so that's nice. We're even going to compute our degrees of freedom the same. Let's do that real quick. Our degrees of freedom should be our number of rows minus 1 times our number of columns minus 1. Here I'm seeing our number of rows was 2. Our number of columns, how many outputs was there for living arrangement? 4. So that's just going to be 1 times 3. So it looks like we'll be using 3 degrees of freedom associated with this once we go to get our p-value. But so far, all we've done computationally is we've only computed 1 out of the 8 necessary expected number of observations. Then we have to take those 8 expecteds, compare them with the 8 observed to get the 8 Pearson squared residuals, and then add up those 8 numbers. That'll get us our chi-squared test statistic that we can use with the degrees of freedom to compute a p-value. So that's just to say there's kind of a lot of multiplication and addition that we still need to do coming up here, and which is why I'm going to let Excel do it for us. So what I'm going to do is I'm going to copy this table. Ooh, I don't know if it's going to, let me get rid of this highlighter right here since I don't know if it's going to like that. I definitely don't want that over in Excel. I'm going to go ahead and copy this guy, and we're going to head on over to Excel. I am going to leave that in there though for our visualizing purposes. And let's head on over to Excel and have Excel do all this type of computation for us here. So here we are in Excel. So I'm going to give us our test for homogeneity. And I'm going to try and do like a really nice clean job in Excel here, by the way, so that we can kind of like reuse this, or kind of you guys can make the most use of this. So let's throw those guys in there. And is there a way for me to clear all formatting? I don't know if I can do that. I don't think I need this to be huge right here at least. So let's at least drop this down to our typical sizing right there. So we've got, and I'm going to kind of copy over some information real quick here just to make sure that we can still kind of read this and talk about this. So this was our dorm. This was our apartment, parent, and other. Okay. What we know is that first things first, I kind of need to get my row total, column total, stuff like that. So I'm first going to go over here. And by the way, you're going to want to watch the Excel computations that I do. I know some of us are pretty okay at Excel by now. I know that some of us really struggle with Excel. I'm not going to do anything really, really crazy here with Excel, but I am going to ask it to compute like every number that we want right here. So just like really try and follow along. This is me reducing the work that you need to do for sure. All right. So first thing I want to do is I want to add together these two numbers here. Notice that I could totally just do equals 72 plus 91. There's nothing really wrong with that since it's just two numbers. Alternatively, the more Excel way to do things would be to say the sum of, here I have C10 through C11, using that colon to separate them right there. And we can see highlighted in blue, it's obviously selected the numbers that we want, stuff like that, right? So, oh, and by the way, actually, I can, now that I've done one computation that worked just across a row right there, I should now be able to drag this guy out this way. And notice that you can double click to confirm what it did. That did the sum of D10 to D11, which is exactly what I want. Oop. This did the sum of E10 to E11, exactly what I wanted. Over here, similarly, I'm going to do equals sum. What's my sum here? It looks like B10 through E10. And again, I can now drag this down and it will equivalently figure out my associated parts I should have there. And notice I can even drag it down in the bottom right, because in the bottom right, it will just say add up across this bottom row down there, and it'll add up that row and get me the 550 I knew to expect right there. So I at least see some numbers I recognize: 163, 250, 300, 550. Those were all numbers we saw before. So I feel pretty dang good that we're getting stuff that matched what we had before, right? So now what I think I want to do for myself, this is my, here's what I should do. Let me go ahead and insert, and I'm going to say, this is our observed counts. Now down here, let's go ahead and do a similar thing. Expected counts. All right. I am going to grab all this table, but we'll delete the information that's in it. All right. So what we want to do now is we want to compute this expected value as the row total times the column total divided by the total total. I don't know how much easier. There's probably a pretty slick way that we could do this in Excel. Let's see if this works out for us here to do it like this. So I'm saying for this guy, this should be my row total, which should be F11, times my column total, which should be B13, divided by my total, which should be F550, or F550. I want it to be 550. It should be F13. Right? Now, if I try and drag this out, is it going to do, like, let's just try it and see what we get. Oh, it gave me division by 0. Why did it do that? Ah, it did move those two. All right, so there is certainly a way to fix this. If you guys are decent with Excel, this really isn't too crazy of a thing, but I don't think I want to get crazy into any type of Excel deeper things right here. So I think I'm just going to write these out by hand. It's not too bad, at least when we're typing them here. So my row total, 250, times column total, 163, divided by total, 550. For this guy here, apartment, row total, 250, times column total, 170, divided by total, 550. Equals parent, we've got 250 is the row total, times 137 is the column total, divided by 550. And for the last one here, row total 250, times column total 80, divided by 550. And now we'll do the exact same thing here. Can I not just, oh no, I didn't reference anything in there. So now for female, we're going to get the same thing, but all the 250s are going to be replaced with 300, right? All the 250s are going to get replaced with 300. So this is going to give me now row total 300 times column total 163 divided by 550, right? Again, I just looked at this cell here, 91. It had a row total of 300. It had a column total of 163. All of them have a total of 550. For the next guy here, row total 300, column total 170, total 550. Row total 300, column total 137, total 550. Last one, row total 300, column total 80, total 550. So not too bad right there. Still a little bit annoying. Yeah, Claire, good call. So I can change the. So you're making a good call. What are the parts that are staying the same? What are the parts that are staying that are being different? The row totals are staying the same across each row. The column, or it's the column totals that are changing a lot. If you're interested, when we do things like reference like cell C16, you can use dollar signs to say and never change that number right there. The dollar signs say don't adjust it when you drag it across a row or a column, and that's how we can keep it fixed at like always having a 550 in a slot, always having a 250 or 300 in a slot right there. So all we'd really need to do is just add a couple dollar signs, and it would keep some of them fixed while letting others change as we slid around. It's not really hard to do. I don't want to discourage people from using Excel, and still typing out those 8 things right there was super, super easy for me. So now let's do this one more time, because now we have the observed and the expected. Now we want to do all of our O minus E squared divided by E, and we should get 8 numbers, and we want to add up all 8 of those numbers to get our chi-squared test statistic. So once again, I'm going to copy the table so I can get a blank version of it. That right there. And now I will call this our, oh, I think I went one further than I needed to. Now I'll go ahead and call this our equal, that's not equal to. Um, This is just remember, this is just the name of that observed minus expected squared divided by observed. So again, I'm going to go ahead and clear out this table. So I have just a blank table. And on this one now, I think I'm going to be good to go to just drag my calculation across. So I'm going to go ahead and actually use the referred to information here. So this one, my observed, so I want O minus E squared. So I'm going to do my observed counts is sitting up here. Oh, I can just click it. I forgot about that. Minus my expected counts. That's sitting right there. Squared. All divided by my expected count, also sitting right there. And that will give me my contribution from this one. Now remember, we said, holy cow, we were expecting 74 and we got 72 out of 550. That like basically nailed it. Like this 72 was very, very accurate relative to our null hypothesis that these distributions should be the same. And 72 pretty much hit it right on the head. And so notice we're getting a tiny contribution to our test statistics saying this contributed almost no difference relative to our suggestion that these distributions are the same. This represents a very little difference from our null hypothesis. So what I think I can do now is I think I can drag these guys out and we're gonna want to double check some of them, by the way. Oh, it looks like it only wants me to go one direction at a time. That's fine. So let me check this one. This one now says B12 minus B18 squared over B18. It looks like it did the correct things. It grabbed all the bottom left cells and it put it in the bottom left cell. So I feel good about that one. And now I can highlight both of those groupings and I think I can drag them across right here. And again, we should spot check these guys. This guy, yep, it looked like it grabbed the terms from the correct relevant cells right there. What about this guy? Yep, it grabbed the upper right cells, put that information in the upper right cell. This color coding in Excel, super duper useful for just those little checks right there. So again, notice I only had to type this out once, and then I was able to just drag it across all the rest right here. So here's all the individual contributions. So here's a thing I can observe before I move on. One thing I'm observing is that this cell, male parent, seems to be the one that's most out of whack relative to our suggestion that the distributions are equal between male and females. This says to me, notice that we've got only 49 but 88 right here. This says to me there's like, oh man, it's like almost like double, almost twice as many females live with their parents. But over here, we certainly weren't sampling almost twice as many females, right? So what I'm seeing here is that these two, in fact, are the greatest contributors to our chi-squared test statistic. Out of the 8 terms we're adding up to get chi-squared, those two are the biggest, saying these two are the most far off from us having having equal distributions across our two across male and female. On the other hand, the dorm living status seemed to match the most closely with what we expected. Expected 74 got 72, expected 89 got 91. That really closely matches, and therefore these terms make very small contributions. They're saying this is, in a sense, how much difference did we see from what we expected? A little bit. Here, this is saying, how much difference did we see from what we expected? Kind of a lot, or at least more than anywhere else out there, right? So now all I want to do, that we've got all of our information put together, we can now say let me say sum all 8 cells, and this will give us our, let me write it like this, so that we have a nice visual here. Sum all 8 cells. Oh, don't do that. Oh, come on. It's not a formula. Just leave it alone right there. Seriously won't let me do that? No, I'm not. Did I type equals at the beginning? I hate you sometimes, Excel. Goodness gracious. So chi-square test stat. And this will be equals the sum. And notice that a sum doesn't just have to be a row or a column. I want the sum from the upper left all the way down to the lower right there. And notice it's highlighting all of them. From B23 was the upper left, down to E24 was the lower right. I'll wrap that guy up, and that'll give me the sum. So this is our chi-squared test statistic. And so we can now compare this with our degrees of freedom. We saw we already computed this back in Microsoft Word, right? Our degrees of freedom, it's our our number of columns minus 1 is 3. Our number of rows minus 1 is 1. And 1 times 3 gave us 3. So I have my chi-squared test statistic, I have my degrees of freedom, and so now we can go ahead and compute our p-value. And our p-value will always be R1 minus chi-squared dot dist. What does it want first? Our chi-squared test statistic, that's sitting in E26. And next it wants our degrees of freedom, that's sitting in E27. And cumulative will always be true. And this is going to tell us that p-value looks a whole lot like the p-value that we computed in our previous example, actually. It's just a coincidence right there. But we've computed a p-value. This is saying to me, it seems like if we were to do this whole experiment again, sample another 550 people, another 250 males and 300 females, then what we should see is that there's only about a 1.75% chance that we would see results that differ from equal distributions as much as this differed from equal distributions. That says to us this is a pretty extreme, pretty rare event right here. We were willing to see an event that was going to occur at most 5% of the time in rarity. We got something that was as rare as 1.75%. That's more rare than our rareness cutoff. So it does look like we'll be rejecting the null hypothesis once again. And concluding the alternative hypothesis. So I would like to grab this and put this, I want to put a screenshot of this in our Word document here. So let's go ahead and do that. Ooh, I see what I need to do first here though. I do want in here, I want those columns at the top. So I want you guys to be able to see what the ABC stuff is like that so that you can see where we use these numbers from. Okay, now I'm ready to take my snip here. So I think that's all we got to be able to see right there. All right. Copy that guy, bring it back into Word, bring us back into Word. Here we are. All right. So we just did all this. So it looks like we came up with, just fill in some information by hand here. We found oh my gosh, I just found all my colors in here. But I still can't write with them. Seriously, just let me. I don't want editing tips. I really don't. Can I turn off editing tips? Is that not up? Nope. Okay, well in a minute, once I figure out how I'm allowed to draw again, I select the marker, doesn't want me to draw. Is there something I'm doing? I don't know. Oh my gosh, I didn't do anything different. I just didn't do anything different here. Okay, we have our chi-squared test statistic. We found that to be 10.12, just call that 9 right there. We found our degrees of freedom to be 3. We used these together to compute our p-value, 0.0175. And so we are now prepared to compare and conclude. And I think this will be nice and easy for us here. At the alpha equals 0.05 level of significance, our data are significant. They are statistically significant. We saw not just a difference, but we saw a difference that we do not believe happened by chance. We saw a difference that we believe happened because there's actually a difference in distribution between male and female living arrangement. Our data are our data are significant. Holy cow, I'm dragging this out as much as I can. With a p-value equal to 0.0175. So we reject the null hypothesis and conclude that there is a difference in distribution of living arrangement between male and female college students. All right. So we have found that there is a difference because we saw it is very unlikely, p-value 0.0175. There's only a 1.75% chance that there's no difference in distribution and we just got a weird sample. We're saying that this is a unlikely enough chance that we don't think that this was just a weird sample. We actually think that the distributions don't actually match each other because this was over our threshold of 0.05. This was more unlikely than we were willing to accept for unlikeliness of a sample. And so we have rejected the null hypothesis. And again, kind of notice that one thing I want to just suggest to you guys to be careful about is that the computation that we do in the test for homogeneity and the test for independence are identical. We're computing our expecteds as the row total times the column total divided by the total total. We're adding up all of the squared Pearson residuals over here to get our chi-squared test statistic, p-value computations the same, all that stuff. But remember that these tests are doing two different jobs. Remember that this expected computation it's the exact same computation, but it came from a different place, sort of. The reason that it's the same, or sorry, the reason that it is this in one case is not the same reason as it's that same thing in the other case. So you don't necessarily have to worry too much about that, but just know that these aren't the same test. These tests are doing two different jobs. One was a test between two variables to determine if the variables were independent. Another was a test between two populations to determine if the two populations have the same distribution of one variable. The job that these tests are doing is very similar, or sorry, very different. Two samples, one variable versus two variables, one sample out there, right? So here again, we're trying to make a judgment about a distribution, and so that's what our conclusion states. In the previous example, we were looking to make a conclusion about independence of two variables, and therefore that was the conclusion that we made there. So again, kind of the good news for you is the math between these two things that we covered today is almost identical. The math is identical weirdly for different reasons. But our conclusions are very different, right? And our setups are very different. So maybe I'm going to leave you guys as my parting statement for the day is don't forget the differences that we're seeing right here. There are two variables, or sorry, in this case, only one variable was collected from two separate groups, right? What didn't happen here is we didn't just take a random sample of people and ask them if they lived in dorm, apartment, parents, or other. We took a sample of males first, then we took a sample of females second. That's different from our previous example here, where we just took a sample of people and we asked those people two questions about two variables, right? So that's kind of our big essential difference here. Was this one population with two variables, or was this two populations with one variable? If we have two variables, we can determine if the two variables are independent of another. If we have two populations, we can determine if those populations follow the same distribution for the one variable that's being considered here. All right. So I guess my last comment for the day for you will be you should become friends with Excel. Doing things like this made me know that I was doing things correctly. It was minimizing the amount of by hand work that I had to do. It's easily mimicable in future situations when you are looking at lots of problems that look like this, for example, in my open math. This is very repeatable right here. So set yourself up to not do 1 million by hand multiplications and additions over this chapter right here. I think that it is in your best interest to get comfortable with either Microsoft Excel, which again, go to Redwoods or Google for Redwoods Microsoft Office and you can download it for free. Or you can use Google Sheets, which isn't that the version of Google Docs out there, right? So there's a couple different free spreadsheet applications that you have access to. If you haven't been using them, I think it's probably nice for you to use them. I'm saying this to you because I want you to do less work. Don't just do more work because you're doing things by hand and you don't want to learn Excel. Just learn a little bit of Excel and it will make your life a little bit nicer for you. And certainly hit me up with any questions about that. So that wraps it up here today for our tests for independence and for homogeneity. Computations match, interpretations and setups don't match right there. So make sure that we can distinguish between the two. We have Thanksgiving break coming up this coming week. We will be picking up after Thanksgiving break by looking at our tests for variance and seeing if seeing if a sample has a certain variation or not, a standard deviation or variance or not. Also notice I am going to sort of post I just don't want to call it a test. I sort of like to think that what I'm going to be distributing to you guys on Friday for Thanksgiving break and for the beginning of the next week is not so much as like a test as like a written homework that covers the last 3 or 4 weeks of this class since we haven't really had any out there. It's still the case that I'm going to expect that you guys don't work on this together, but I don't want you guys to be like, oh, I've got like a test I have to do. You should think of this as just like a long form handwritten homework here that you guys will submit to me the week after Thanksgiving. I would encourage you guys to work on it over Thanksgiving so that you don't feel rushed and so that you do feel that you have enough time to do this. But on the other hand, if you are saying, I will do no work for the 5 days of Thanksgiving break, then it should be plenty of time for you to knock this guy out on the weekends and on Monday of Tuesday of our week after Thanksgiving. It won't be due until midnight on Tuesday of the week after Thanksgiving. So if you are going to insist that you will do no schoolwork, I'm always like, you shouldn't do that, but also I'm sure that's what I did when I was an undergrad. So in any event, I'm trying to distribute this so that if you want to get ahead of this and just crush this on Monday, Tuesday of Thanksgiving, go for it. If you want to wait until the week after, you can also wait. But I will put out sort of a long form homework assignment that's sort of like a test, but more like a homework assignment in my mind. And I'm hoping that's what it'll be like in your mind as well. So have a good one, everybody. And I will get that thing posted on Friday of this week. And I will see you again in 2 weeks as we wrap it up. And remember, after Thanksgiving, we have 2 weeks of lecture and then finals week. So I will see you guys for our conclusionary couple weeks after Thanksgiving here. Have a good one.